I guess let me. So suppose I do this and this, but then the top. Let me see. So. So I kind of have opposite gluings on both. Okay, so I do this. So that's another surface. Okay, and it turns out, so this one is also non-orientable, right? So it's non-orientable. Why? Because it has an embedded Mobius strip, right? So this guy is a Mobius strip sitting inside here. But if you look at its Euler characteristic, so Euler characteristic is equal to 1. Okay, so maybe I'll put that in as an exercise. Okay, so you can just count the number of edges and number of vertices, etc., that you get after gluing, and then you'll find it. So this is a different non-orientable surface than the Klein bottle. Okay, and this guy has a name. This is called a projective plane. All right. So it turns out that, so here's, let me just sort of mention, I was sort of with the fact that, so this is something called the classification of surfaces. So all surfaces can be sort of topologically, up to topological equivalence is characterized by whether it's orientable or not and what its Euler number is. Okay, so if two surfaces have the same, this is it's a theorem. It's something that will come, maybe at the end of a first course in topology or something. Okay, so it involves some, the proof will involve some more ideas, etc. So two surfaces have the same Euler number and orientability. So in other words, either both are orientable or both are non-orientable, then they are topologically equivalent. Okay, so this is sort of like the converse of one direction that we already saw. We already know that if things are topologically equivalent, if they differ by just deforming one to, then the Euler number doesn't change, and neither does orientability, right? If some Mobius strip is embedded in one, it will remain embedded in the other because you've just stretched things around and moved it around. Okay, so the other direction is easy, but in fact, once you know the Euler number and whether it's orientable or not, you actually know what the surface is. Okay, topologically. And this is sort of kind of an interesting thing. And it turns out, right, so these are the ones that we saw today. These are the sort of the simplest surfaces, right? So things that we've seen so far, the sphere, the torus, these are sort of the simplest orientable surfaces, and the projective plane and the Klein bottle are the simplest non-orientable surfaces. And then you can build more, right, by sort of I'll mention it next time, but you can add handles, just like we saw a glimpse of it last time. You can add handles to make higher sort of number of holes. Okay, so you decrease Euler characteristic each time. And the other, with that way you can make orientable surfaces, and you can make non-orientable surfaces by sort of cutting out a disk and gluing in Mobius strips. Okay, so these Mobius strips form a sort of a basic building block in some sense of these non-orientable surfaces. Okay, so just like we saw, if you glue two Mobius strips, you get a Klein bottle. It turns out that if you take a Mobius strip and glue a disk to it, right? So this is my Mobius strip, and you glue a disk to it. Disk also has one boundary, and you glue that to the edge of the Mobius strip, you get a projective plane.
So I have a question. I could not understand how you built up the Klein bottle, the arrow thing. Yeah, yeah, yeah. This one,
Okay,
this one. Yeah. Can you
right.
repeat it? Yeah, yeah.
Yeah, so the Klein bottle, you take a start with a square piece of paper, just as before, right? And then you glue the top edge to the bottom edge, just like you did in a torus, right? But this time, the left edge and the right edge, they are glued with a twist, right? So when you have this cylinder. Let me show you that animation again. Um, oops. Right. So this was the animation, right? So when you glue this edge of the cylinder to the other, you have to twist it around. So here, instead of kind of twisting, when you twist, you have to pass through. Okay, so that's how you get something which is a Klein bottle. So it's sort of harder to imagine that, or doing it on the in R3, actually doing it with paper, but so it's easier to just draw a picture of it. And to treat it as a topological space. So as a topological space, it's the same as this square piece of paper with the identifications as shown. So once again, if you look at this point is now the same as this point, okay? Because so instead of a torus where it was same as something which is diametrically opposite, right? So it's just a cross. So this time you have this change of the direction. So this is sort of closer to the top side of this left hand side. So on the right hand edge, when it's identified with this half twist, it's sort of identified with the bottom, closer to the bottom, right? So so if you're an ant on this Klein bottle, and then you kind of go towards this orange guy, and then you find yourself in the orange spot, and you find yourself coming out of here. Okay, so this is topologically, this is the space that you have constructed, right? So is that clearer?
Yes, just one more thing. You said that the vertices over here.
Yeah,
Hello?
yeah,
The
I can hear you.
vertices, they kind of merge. Like
Yeah, they're
the four
identified, right?
vertices
Because
we
when you
have on
glue,
this.
yeah, so that happens even for a torus, even here. So when you glue the top edge to the bottom edge, then this guy, let me use some other color, let's say this purple. So this guy is identified with this when you glue this top edge to this bottom edge, right? So these two vertices are the same. But then when you look at
Yes.
the one on the right hand side, when you glue this left edge to this edge, well, then these top and bottom are glued to the bottom and top again. So if the things that those vertices that were the same are also the same here. So after gluing up, all of those get identified to a single point. That happens even when you glue on a torus. When you have these four sides on a torus, let me actually draw it. So if you have a torus, this is again for a torus. So, and then you glue this side to that and this to this, then these vertices all get identified, and you can see it on a torus. On a torus, what you see, you have this single vertex, and then so after you do this gluing, you will actually see this edge and this edge. So this will be, let's say, our double edge here, and this will be this edge. So you will see a single vertex. After gluing, you will get a single vertex. All right, and the same thing happens here.
And
Okay.
sir, the torus also has two edges.
Yeah, that's right. Yeah, torus also two edges. Euler number of a torus is also 0, right? We saw last time.
Yes,
So
yes.
yeah, so the Euler number of torus and a Klein bottle are the same, but one is orientable and the other is not. Okay, and that's the difference. So topologically, they are not equivalent spaces. Okay.
Yes, sir. Yeah, yeah.
Yeah.
Thank you.
Okay. Yeah. All right. Any other quick question? Somebody says, will Klein bottle intersect itself in higher dimensions? Yeah, I guess you kind of can guess the answer. You can. So if you try to build a Klein bottle in R3, in our space, then you have to intersect. But if you're in higher dimensions, then you don't need to intersect, right? So because you have more room to pull it pull it out in another dimension. So this is something that you probably can see see some movies of or something on YouTube. But yeah, so in general, higher dimensions somehow have more space to move, right? So you can sort of pull apart things which intersect. So just like on the plane, you might have two lines intersecting, right? You can't cross from one side to another, without intersecting. But if you have one more dimension to move, right, you can just push your line, away, and then you are not intersecting. So you can do this in any dimension actually. Yeah. So I guess we are talking of two dimensions most of the time, these couple of sessions, because it's easiest to visualize and you can draw pictures of. But topology, we deal with any number of dimensions, and so there's a lot of interesting things going on. And in higher dimensions, there are versions of the Euler number. I guess somebody was asking about that last session. It was so there are so instead of sort of vertices and edges and faces, you might have things of faces of higher dimensions, and then you have to count them and take an alternating sum. That turns out to be a topological invariant. Okay, so these are things that one learns in algebraic topology. Okay, and a little bit later when one.
The thing is, we saw that the Klein bottle intersects itself in R3,
Right.
Three-dimensional space. But I mean, I know that it does not. I'm told that it does not in four-dimensional space.
Right.
But I mean, you said that it does not intersect in higher dimensions. So it could be that it does not in four dimensions and it does in some nth dimension, which is greater than 4. But how do we know that it does not in fourth dimension?
Yeah. So right. So it does not, because I mean, so the point is that so you can imagine it by saying, so this is sort of one way of saying it, that so you can color this. So see, it's harder to sort of so you can't picture the fourth dimension, but you can represent it, let's say, by a color with a shade of red, let's say on the Klein bottle, right? Okay, so the more red you are, the greater the coordinate in that fourth the dimension is. Okay, so now when you kind of have this picture of a Klein bottle intersecting itself, you can make it more and more red as you go to approach the intersection. All right, so it's a Klein bottle, which is the way that it's described in topology books is that you kind of, at least in one topology book, I don't remember which one, is that the Klein bottle blushes as it intersects itself. Okay, so it's kind of more red when it intersects itself and comes up. So this since it's more red, it's in the fourth coordinate, it's somewhere else because it's farther apart. So it's sort of the part of the surface that it seems to intersect in R3 is actually nowhere close in the fourth dimension, because that's less red than the other part that is intersecting. So this way you can actually sort of visualize the fourth dimension in this particular setting. Of course, it gets harder as you want to visualize more and more dimensions, but fourth dimension, usually you can kind of imagine it in sort of by shade of red, or sometimes it's like a movie, so that you have a time is the fourth dimension after all. So you can sort of view the shapes as movies and so on. So there are ways to see that a Klein bottle can be embedded in R4. Okay, so and yeah, so if something is embedded in R4, it certainly can be embedded in all higher dimensions. Yeah. Okay.
Thank you, sir.
Yeah.
Thank
good.
you so much.
Great. Okay, fine. So next time we'll talk about a bit more about what topological equivalence really is. I've been talking informally about that, so we'll talk a little bit more formally about topological equivalence and say sort of maybe what a surface is also. So sort of I've been talking informally what a surface is and what a surface mathematically actually is. And then we'll move on further. I hope you're kind of also reading up on these things from various places. Maybe Armstrong's book is a good one. Somebody's asking, is there a tool to see what shapes look like in many dimensions? Well, I mean, unfortunately not. I mean, it's difficult to visualize, but you can visualize slices of it, right? You can project, you can have shadows of a higher dimensional thing to 3 dimensions or 2 dimensions and look at those. And but mathematically, you can always work with if algebraically, right? In terms of symbols, you can write down the equation of an n-dimensional sphere, for instance, right? And just like a circle is x1 square plus x2 square equals 1. A 3-dimensional sphere, sorry, 2-dimensional sphere is x1 square plus x2 square plus x3 squares equals 1. These are what we learn when we're doing, let's say, physics or something. With n-dimensional spheres, you just add up x1 square plus to xn plus 1 square. You have n plus 1 variables. It's sitting inside Rn plus 1 square equals 1. Okay, and you look at so abstractly, you can define the sphere as the set of points in Rn plus 1 which satisfy this equation. And this, makes perfect sense symbolically. Okay, and so mathematicians can work with that. And there's no need to really visualize. We can try to visualize, think of a 2-dimensional sphere and sort of try to think of it as an analog of that. But our human minds can't really, I mean, since we are only used to 3 dimensions, you can't really process something which is, sort of 10-dimensional or 15-dimensional. So you have to rely on mathematical symbols and things like that. Okay, fine. All right. Okay, folks, see you next time.